Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So for chapter number 4, part number 1, we will discuss about axial flow turbines. In terms of content for axial flow turbine, we will discuss about velocity diagram, thermodynamic of axial turbine, stage losses and efficiency, stage reaction, deceleration of flow, turbine stage efficiency, and the last one, turbine blade cooling system. For axial flow turbine analysis, we need to know what I call the basic concept of velocity diagram, because later on we will use velocity diagram to determine various value of parameters such as efficiency, degree of reaction, and so on. So we need to know how to draw velocity diagram for the axial flow turbine. Okay, before we discuss about the velocity diagram, let me discuss about the basic features of axial turbine stage. What is the meaning of axial turbine stage? Okay, the figure shows the arrangement of the compressor, main component of the gas turbine engine, that consists of a compressor, combustion chamber, and also turbine. For a turbine, the turbine will consist of two main parts. First, we call rotor, which is referred as the moving blades, as shown in the figure, and sometimes we call buckets. So buckets also represent the rotor in the turbine. And the second part, or the second component, important component in the turbine, we call the stator, which is referred as the static blade. So the stator is the component that doesn't move or doesn't rotate in the turbine, as shown in the figures. So this figure shows the actual stator of the turbine, and the stator also called the nozzles, or sometimes we call fixed guide vanes. Okay, the same component but with different names. Okay, so now the diagram shows the cross-section drawing, 2D drawing of the rotor and also stator of the turbine. So we have a rotor, and on the rotor we have rotor blades. So the rotor will attach with driven shaft in order to rotate the rotor. Also we have the second component, the stator, and the stator. On the stator, so we will have stator blades. So the stator blades will attach at the casing. That's why the stator doesn't move. Okay, so now we look at 2D view of rotor and stator blades arrangement. Okay, so we have example of rotor and also nozzle or stator. So in this figure we have two row of rotor and also one row of nozzle. So for rotor, so we will have blade speed U, because the rotor rotate, and so we need to have blade speed of the rotor, which is also represent the rotational speed of the rotor. And for nozzle or stator, there is no blade speed because the stator or nozzle doesn't move in the turbine. Okay, the blue color arrow represent the gas flow direction or the gas flow vector. Okay, so the arrow shows the direction of the gas flow that flow through the rotor, nozzle, and also rotor. So the process will be repeating in the turbine until at the end of the of the turbine. And The arrow also represent the vector of the flow. Normally we refer in turbo machine, we refer as C. Okay, part of the blade as shown in the figures we call a turbine stage, where in terms of definition, a turbine stage is the what I call consists of one stator and one rotor, as shown in the schematic diagram. So normally for analysis of a stage, of a turbine stage, we consider one stator and also one rotor. So we just take a few sample of the blade in our schematic diagram. So normally for turbine we will start with stator and then rotor blade. So in the figure shows the parameters such as S, which is represent the spacing distance of the two identical blade. B represent the what we call the rotor thickness, and U is the blade speed. So we only have the U vector just for the rotor because the stator doesn't move, so we don't have U which is referred as blade speed for the stator. Okay, so now if you refer to the diagram, if you rotate the diagram, so we will get the second diagram, same diagram but different orientation. Okay, for the last figures we will use these figures throughout the chapter. So for consistency, so this diagram will be used throughout the chapter in our velocity diagram analysis. Okay, for velocity diagram for axial turbine stage, there are two basic concepts that we need to know. First concept is the vector concept. Okay, as we know, a vector, for example vector A, we'll have the length of the vector A represent the magnitudes, and the angle of the vector A will represent the direction of the vector. Okay, so if we have two different vector, for example vector A, and we add with vector B, so we will have a vector that we call the resultant vector, which is equal to vector A plus vector B. So we need to look at the direction of the vector A, vector B, and also vector of resultant A plus B. Okay, so the direction of the vector is important. If we refer to the parallelogram law of the vector, instead of we have vector A plus vector B equal to R, resultant vector, so we also can make it what I call the vector in terms of resultant vector as vector B plus vector A. So the result will be the same. Okay, the resultant vector for vector B plus vector A actually same as the resultant vector for vector A plus vector B. Okay, the second basic concept that you need to know before we study, we discuss about the velocity diagram for the axial turbine stage, is about the difference between absolute velocity and also relative velocity. For example, we have a boat that want to cross a river. Let's say for the first condition, we assume that in terms of call river flow velocity is equal to 0, so no river flow for the first case, and the boat across the river at certain speed and at certain direction that represent by vector W. So this vector W actually refer to the boat velocity set vector when the river flow, which is referred to U, is equal to 0, and this vector refer as the relative velocity vector. However, when we consider the river flow velocity that represented by U, So now we need to add vector W with vector U. Okay, so we need to implement the vector concept, and as the result, so we will get new position of the boat due to the river flow velocity that present during the process. Okay, so we will have resultant vector that represent by C. So C represent boat velocity vector when we consider river flow velocity. Okay, so C vector for this case refer as the absolute velocity, which is the actual velocity vector for the boat. Okay, another example. For example, in the soccer game, so we have a player hit the ball at certain direction and also certain speed value as shown in the figure. So at this condition, without any obstacle or without any other striker that hit the ball, so the ball will follow the direction of W vector. So for this condition, the ball will go out from the field. Okay, so the W vector represent the relative velocity. So now if we consider what I call the involvement of another striker, so when this the striker hit the ball with U speed, okay, so the ball will go into another direction, because after we consider the speed of the striker hit the ball. So when we consider the striker speed, so we will get new vector that refer as vector C, and this vector C is refer to the absolute velocity or the actual velocity of the ball, and the result will be different. So the ball will enter the goal. So that the difference between absolute velocity and also relative velocity. So we can summarize that the relative velocity is the condition, the velocity when we neglect the obstacle, any obstacle such as the resistance and so on. However, the C vector or C velocity represent the actual velocity after we consider resistance and so on. Okay, I hope you are clear about the vector concept and also the difference between absolute velocity and also relative velocity. So now we implement the vector concept and also the absolute and also relative velocity concept to the axial turbine stage. So we have a stator or nozzle blades arrangement and also the rotor blade arrangement. So for the rotor, so we will have U vector because the rotor move with certain rotational speed. So U represent the blade speed. So state number 1 represent the inlet condition of the stator or nozzle. State number 2 represent the condition at the outlet of the nozzle, and also the condition at the inlet of the rotor. And state number 3 represent the condition at the outlet of the rotor. So at the inlet of the nozzle, so we'll have vector C1. Okay, the absolute velocity C1. So we will not have the relative velocity because the stator, or nozzle doesn't move. So we only have the absolute velocity, which is referred to the vector of the fluid enter the stator. Okay, the angle, the direction of the fluid flow enter the stator is represented by alpha 1, the flow angle. Okay, and next at the outlet of the stator, so we will have the relative velocity W2. Okay, so normally the direction of the fluid in terms of relative velocity at the outlet of the stator is depend on the shape of the nozzle blade profile. Okay, so now because and in terms of angle, the angle of the relative velocity vector is represented by beta u, and we call beta is equal to relative angle. So because we only have very small gap between the stator and also the rotor, so the velocity or the blade speed of the rotor will affect the condition or the velocity diagram at the outlet of the nozzle. So now we need to include, for velocity diagram at the outlet of the nozzle, we need to include the vector u for the blade speed. Okay, so by implementing the vector concept, so we have two vector, so we add two vector, vector w2 relative velocity 2 plus vector u, so we will get resultant vector that represent by c2 absolute velocity at the outlet of the nozzle, and the angle we refer as alpha 2, that which is referred as the absolute angle. Okay, so due to the small gap of the stator and also the small gap between the nozzle rows and also the rotor rows, so the velocity diagram at the outlet of the nozzle actually same as the velocity diagram at the inlet of the rotor, so we can use the same velocity diagram. Okay, exactly same velocity diagram. And at the outlet of the rotor at condition number 3, so we'll have a correlative velocity vector of the rotor w3, and the direction will be referred to will be depend on the shape of the rotor blades. And because the rotor involved is blade speed vector, so we need to add w3 or relative velocity at the outlet of the rotor plus the blade speed vector u. So implement the vector concept, so you will get the resultant vector that represent by c3, which is referred as the absolute angle, absolute velocity at the outlet of the rotor, and the angle for the absolute velocity is alpha 3. For the relative velocity at the outlet of the rotor, the angle referred as beta 3. Okay, so if we need to draw the turbine stage velocity diagram, actually we can combine both the diagram, the velocity diagram at the inlet of the rotor at condition number 2, and also the velocity diagram at the outlet of the rotor at the condition number 3. Okay, why we can combine? So we can combine this diagram because for the same rotor, the blade speed is the same, which means we will have the same vector of u. So that's why you can combine what I call the two velocity diagram at the inlet and also at the outlet of the rotor, because the distance or the length of the vector u is the same, so we just combine, so we will get the complete turbine stage velocity diagram for the rotor. Okay, velocity diagram condition for axial turbine stage. So before we discuss about velocity diagram condition, let me look about the turbine stages. So the diagram shows the figure shows the schematic diagram of a turbine that consists of numbers of stator rows and also numbers of rotor rows, and the figure shows the direction of hot gas flow in the turbine. So if you look at the 2D view of turbine stages, The stages will consist of numbers of stator and nozzle and numbers of rotors. Okay, and diagram also shows the direction of fluid flow or gas flow that flow throughout the turbine, as shown by the pink color arrows. So the first nozzle and also rotor we consider as the first stage. So if the turbine only have one stator and one rotor, we call the turbine as a single stage turbine. And the final I call the combination of stator or nozzle and also rotor at the end of the turbine, we call the final stage of the turbine. Okay, so the stage between the first stage and the final stage we call end stage. Okay, there are few conditions that are considered in order to simplify the analysis involved with the velocity diagram. So the first condition is the condition for a single stage and also for the first stage of the turbine. So for the first condition, we can implement this condition for the turbine that only have a single stage. So the turbine only have one rotor and also one stator, or we can implement the condition for multi-stages turbine, but the condition we only apply for the first stage of the turbine. So for the condition number 1, we assume that the condition of flow at the inlet is axial absolute velocity flow condition, where we have C1 vector with alpha 1 equal to 0. Okay, so we have axial absolute velocity condition. Okay, so we need to implement this condition in order to simplify the calculation of the velocity diagram. So the condition are shown in the schematic diagram. For condition number 2 is the condition for normal stage condition. So for this condition, we consider in terms of flow velocity and also angle. So we have same flow velocity and same angle at the inlet and also at the outlet. For example, for the end stage, so we have C1 vector with alpha 1 absolute angle. Okay, C1 absolute velocity with alpha 1 absolute angle. And at the outlet of the stage, C3 with alpha 3 in terms of absolute angle. So for normal stage condition, the value of C1 will be equal to C3 and the angle of alpha 1 will be equal to the angle of alpha 3. Okay, the second figure shows the example if we implement normal stage condition for single stage turbine. So as we know, for single stage turbine, we implement the first condition where we have axial flow at the inlet. So if you implement the normal state condition, we also have the axial flow at the outlet of the stage. So C1 equal to C3, where both alpha 1 and also alpha 3 will be equal to 0. So the main criteria for normal stage is the value of C1 at the inlet of the stage equal to C3, I call the absolute velocity at the outlet of the stage, and the angle, the absolute angle at the inlet of the stage alpha 1 also equal to the absolute angle at the outlet of the stage alpha 3. The third condition is the two-dimensional theory condition, where we implement same axial flow velocity component at the inlet and also at the outlet. So this condition actually based on the continuity equation for uniform and also steady flow. Okay, Okay, so we have row 1 alpha A1 cross section of the of the fluid multiplied by Cx1 axial flow component equal to row 2 A2 Cx2 equal to row 3 A3 Cx3. So based on the inlet of the stator, outlet of the stator, and also outlet of the rotor. So implement the two-dimensional theory for simplicity. So we'll get Cx1, the axial flow component, at condition number 1 equal to Cx2 equal to Cx3. Okay, so for two-dimensional theory condition, so we assume that same all the value of axial flow velocity component are the same. We'll use the same value at the inlet and also at the outlet. Okay, for example, as shown in this that diagram. So the diagram show the velocity diagram at the different condition. So at the stator inlet, as we discussed in previous slide, at the stator we have called the vector for C1 at the inlet of the stator. So the C1 vector will have the velocity component Cx1. At rotor inlet, so we have the vector for W2, U, and also C2. So for the absolute velocity C2, so we'll have the x component, axial component for velocity Cx2. Similarly, with the what we call the velocity diagram at the rotor outlet, so we have W3, C3, and also U. So the axial component for C3 vector is Cx3. So if we implement two-dimensional theory condition, so all Cx1 value, Cx2, and also Cx3 value will be the same. So Cx1 will be equal to Cx2, will be equal to Cx3, equal to Cx. So these are the three conditions that can be used in order to simplify the velocity diagram analysis. Trigonometry or triangle law for velocity diagram. So as we know, all vectors that involve in velocity diagram will have x direction and also y direction components. So the figure shows the combination of velocity diagram at the rotor inlet, condition number 2, and also the velocity diagram at the rotor outlet, condition number 3. So each vector in the velocity diagram, in both velocity diagrams, will have x direction and also y direction components vector. So as shown in the figure, the y component for the relative velocity W2 will be equal to Wy2. The y component vector for relative velocity W3 is equal to Wy3. However, for absolute velocity vector C2, the y component for C2 is equal to Cy2, and y component for absolute velocity C3 is equal to Cy3. And when we implement the third condition for the velocity diagram, which is referred as the two-dimensional theory condition, where we assume that the same value of axial flow velocity component at the inlet and also at the outlet. Okay, so by implementing the condition, the value of x direction component for all vector in the velocity diagram will be equal, where Cx2 for the absolute velocity, x direction component for absolute velocity equal to x component for relative velocity. So Cx2 equal to Wx2 equal to Cx3 equal to Wx3 equal to Cx, as shown in the figure. So all the x direction component of the velocity or of the vector, velocity vector in the velocity diagrams will have the same value. Okay, so let's say we want to know a specific value of component in the velocity diagram. So in order to determine unknown components, we can implement the trigonometry or triangle laws. For example, if you refer to the blue color triangle, where we have theta and also the line for x, y, z, so we can use this equation: cos theta equal to x over z, sin theta equal to y over z, and tangent theta equal to y over x. Cosec theta equal to 1 divided by sin theta. Secant theta equal to 1 divided by cosec theta. And based on the Pythagoras theorem, so z square equal to x square plus y square. Okay, we have other equation based on the green color triangle. We have the angle of beta, alpha, and also theta, the line for A, B, and C. So we can use this equation where A divided by sin alpha equal to B divided by sin beta equal to C divided by sin theta. And the last equation based on the green triangle, where C square equal to A square plus B square minus 2AB cos theta. Okay, for example, let's say we want to know the value of I call y direction component of W2, WY2, which is WY2. So we can use this triangle that represented by blue color triangle. And based on the trigonometry equation, we can use sin theta equal to y over z equation, where we have, if you refer to the velocity diagram involved with WY2, so sin beta 2 equal to WY2 divided by W2. So we have component of WY2 inside the equation. So from the equation, we can determine the value of WY2. Another example, let's say you want to determine the what I call the value of blade speed U. So we can involve the green color triangle, and we can implement the last equation that we mentioned before, where C2 equal to C square equal to alpha, C square equal to A square plus B square minus 2AB cos theta. So implement the equation, substitute all the vector that refer in the velocity diagram, where we have U2 equal to W3 square plus C3 square minus 2W3 C3 cos beta 3 minus alpha 3. So because in the equation we'll have the term of U, so we can determine the value of blade speed from the equation. Example 4.1. Figure 1 shows the rotor blades notation for an axial flow turbine. Data for absolute velocity C, relative velocity W, blade speed U, relative velocity angle beta, and absolute velocity angle alpha at the inlet and also outlet of the blade are partially given in table 1. Fill in the blank for the rest of the value in the table. The value must be calculated through graphical method by drawing the actual velocity triangle for the inlet and outlet on the graph paper provided, with scale of 10 mm to 10 meter per second. Okay, solution for example 4.1. Okay, based on the table given, so the data that already obtained are W2, U, beta 2 for the inlet, W3, U, and beta 3 for the outlet. So now, by using the graphical method, you need to determine C2, alpha 2 for the inlet, C3, alpha 3 for the outlet. So you need to draw the velocity diagram at the inlet and also velocity diagram at the outlet by using graphical method. So you need to use a protractor to determine the angle, and also a ruler to measure the length of the line or of the vector. So first, because we already know that the U vector normally in horizontal condition, So just draw the horizontal line, and based on the value given in the table, determine the length of the u vector. So we get the length for 50 meter per second, based on the 50 meter per second value. Okay, from the initial point of the u vector, so use the protractor to measure the angle for beta 2, and also draw the line for W2 that represent the value of 70 meter per second. Okay, so if you measure the angle, what we call at the initial point of the W2, so you will get the same value, which is also referred as beta 2 equal to 40 degree. Okay, based on the vector concept, if you add W2 and also u vector, so you will get the resultant vector for the velocity diagram at the inlet, where the resultant vector represent the value the vector of C2, the absolute velocity vector. And take a ruler and measure, so and then convert by using the scale that given in the equation. So you will get the value for C2 velocity, absolute velocity C2, so around 108.8 meter per second. Take your protractor, measure the angle of alpha 2, so you will get around 61 degree. Okay, the absolute angle at the inlet. Okay, for the velocity diagram at the outlet, so you already know the value for beta 3 and also W3. So just draw by using the protractor, draw the straight line with angle of 45 degree, and the length should represent the value of 100 meter per second, that represent the value of W3. Okay, by implementing the vector concept, we know that W3 vector plus u vector will be equal to the resultant vector C3. And if you measure the length by using a ruler and convert by using the scale given in the equation, so the value of C3, absolute velocity C3, equal to 73.7 meter per second. And if you measure the angle, the angle will give you in terms of alpha 3 equal to 16 degree. So we already got all the answer for C2 108.8, alpha 2 61 degree, C3 73.7, and alpha 3 equal to 16 degree. So all the answer we obtained from the for the question are based on the graphical method, by using the graphical methods. Okay, in order to test your understanding for part number 1, chapter number 4, please answer the question below. What is the meaning of normal stage condition? Question number 2, what are the two basic mathematical knowledge that we need to know for velocity diagram analysis? Question number 3, what is the basic law for two-dimensional theory condition? So you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue is also given in the link. Okay, that's all for part number 1, chapter number 4. Assalamualaikum.